Hello everyone, welcome back to the course. This video will talk about IC design glossary. As I have mentioned before, I'm from Chinese, and English is not my native speak, so my pronunciation may be not right. And I planned this chapter to help you to familiar with my pronunciation of these words. If the pronunciation of these words are wrong, it should be wrong throughout the whole course. So you have to familiar with it. Okay, let's go on. IC represent for integrated circuit. It's a device containing many semiconductor cells. IC is also named as chip. Specification, spec, short for spec. Specification is a file to define the function of a circuit, a design. The file may be a Word file, a Excel file, it's okay. Design house. Design house are companies who design the schematic diagram of a circuit. For example, Qualcomm, AMD, NVIDIA, Hynix. They just design the schematic. They not manufacture the chip. Foundry. Foundry are companies who manufacture the circuit and make it a chip. For example, TSMC, Global Foundry, SMIC. So the two are the relationship of the two are cooperation. The two cooperated to make a chip. GDS2. GDS2 is a file format to record all the information of how to make a chip, how to manufacture a chip. So after the design process is done at design house will hand over a GDS2 file to Foundry, and Foundry will use the GDS2 file to manufacture the chip. Tape out. The process of hand over the GDS2 file from design house to Foundry is called tape out. This is a big milestone for design house. CMOS, complementary metal oxide semiconductor. This is the most used semiconductor technology to manufacture digital circuit. Usually there is N-type and P-type MOS transistors. There are usually N-type and P-type MOS transistors in a logic cell. They are always paired. One N-type cell paired with one P-type cell. So this is called complementary. Wafer. Wafer is a silicon material, usually with a circular shape, which is the circuit manufactured on. I will show a picture of wafer. Okay. This on the right side is a picture of wafer. And die. Die is a rectangle area on the wafer. It's usually the area for a single chip. So you can see this small rectangle areas. This small rectangle areas is the die, and usually a single chip is placed in this area. This is a chip on the other one. And IP represent for intellectual property. Intellectual property is usually a well-designed block with specific functions and is usually expected to be bug-free. Expected, but not sure. Just expected. For example, UART IP, SQL 2 IP, a USB bus interface IP, a CPU core RISC-V, a RISC-V CPU core IP, micro. Micro is a type of a kind of IP block that can't be modified by the end user. If a micro is giving actual code, it's called a soft micro. If a micro is given in GDS2 format, it's hard micro. Digital IC versus analog IC. There are two different types of IC. But I don't know how to explain the difference between digital and analog. You have to find the difference by yourself. Search on Google. Mixed signal IC. This is a chip containing both digital and analog circuit. The real chip we use now is usually a mixed signal IC. There is rarely pure digital or pure analog IC now. So there is also some so in an IC there is always some digital part and some analog part. For example, you have to use the pad, and you have to use the PL, and you have to use the ADC converter. These are analog part, and you have to use the CPU core. You have to use the signal processing unit. These are usually designed in digital part. SoC. SoC represents for system on chip. This is a system containing many function blocks and and can be used in complex situation. Oh no, this is not accurate. Okay, let me read it. SoC is a system which can be used in some real applications and integrated in a single chip. A system is, this means a system containing many function blocks. They are usually connected up by on-chip bus. So, for example, the CPU from Intel or AMD, we can call it a SoC. Or the cell phone chip you used in the cell phone chip you used in the chip you used in your cell phone is an SoC. FPGA represents for field programmable gate array. It's a kind of IC. It contains many logic gates. The function and the collection of each gate can be configured real time. This is the same as you program an embedded CPU, embedded MCU. Okay, logic gate. Logic gate is a basic cell to calculate binary logic or store data. These are some examples of binary logic gate, such as inverter gate, OR gate, LOR gate, AND gate, NAND gate. get to store data, such as latch, flip-flop. Combination logic. Combination logic is a circuit whose output is only related to its input. And sequential logic. Sequential logic is a circuit whose output relates to its input and its previous data stored in flip-flop or latch. So usually, combination logic can do the calculation, and sequential logic can store data and do some complex functions. We will explain them deeply in the later course. In the later sections. EDA, electronic design automation. Electronic design automation. The whole IC design process will involve several EDA tools to speed up the design process. Some Tier 1 EDA vendors, Synopsys, Cadence, Mentor Graphics. These two companies are companies from China. APIC. Improving. So in this course, we'll study some EDA tools, at least the tools for simulation, Relator, and GTK View to debug, to review the waveform. RTL, register transition level. This is an abstraction level used to describe this digital circuit. And the engineers have defined some language to reprint register transition level. The language is Verilog, VHDL, System Verilog, and this one, Chiso. Chiso is a new language. It's come along with RISC-V. High-level HLS, high-level synthesis. This means you can use a more abstract level of language to describe the function of the circuit. High-level synthesis, usually high-level synthesis will code at a high abstraction level than RTL. So after you have coded a high-level synthesis code, you have to use EDA tools to compile it to RTL level code, such as compile to Verilog code. Describe hardware in RTL. Describe hardware at RTL level is the commonly used method now, and this may be the future technology to describe hardware language. To describe hardware, high-level synthesis may be the future. This is the commonly used method today, and this may be the future. Synthesis is the process to translate your RTL description to logic gate. Logic gate is the basic logic cells we used in digital circuit. So this is done by software. For IC design, you have to use design compiler, or RTL compiler, or some other tools to do the synthesis. For FPGA design, you have to use the Simplify, Vivaldo, or Cortex to do the same job. This process is more like the GCC compile process of C code when you design a C language. Late list. Late list is a file with defined syntax. You usually use the word of VHDL syntax that defines the function of a circuit. In late list, there is only cell instance. There is only get cell, logic get cell instance. This file is usually the output of synthesis. Front-end design. Front-end design, including the process of receiving function requirement from marketing, and then write design specification, and implement it in RTL, and verify, and simulation to verify the function. So this course is focused on front-end design, both digital IC and FPGA design. Back-end design. This is also called physical design. The goal of this course is to change the compiled RTL, the late list. This process is to change the compile. Is to change RTL to GDS2 to file. Okay, maybe from synthesis, to final GDS2 files. PPA in digital design, it represent for power, performance, area. These are the three most important criteria for evaluating the quality of a design. This is the criteria for us to tell a good design from a bad design. In the real world, you have to compromise between PPA, between power, performance, and area. If you want to increase one, for example, you want to increase performance, usually you have to compromise on area and power. Okay, let's take a small break here, and let me show you an example on PPA. First, I will give you a small question. The question is, can we find two designs? One design with PPA, with power, performance, area. The three are all good than the other one. That is design A and design B. The power, performance, area of design A are all good than design B. Can this happen? Okay, just think about it. Okay. Yeah, you may think this can't happen, but in the real world, this may happen. So if this happens, which factors will cause the difference? In my opinion, it's the way you solving the problem, the way you choose to solving the problem, the algorithm you used, and the implementation of the engineer, and the EDA tools you used. So I think it will rely on the 4 factors. Okay, that's maybe hard for you to understanding. So I will give you an example. Let's take a small example of. Let's take an example. If you want to invite someone to dinner, if you want to invite your friend to dinner, how will you do that? How will you do that? First, you can send this information. You can send the invitation face to face, or you can send the invitation remotely. This is the way you choose to solve the problem. Face to face, you can drive a car to meet him and have a talk, or you can take a plane if the distance is far. For remotely method, you can write a letter and post it, or you can edit a short message, or you can write a email, or you can make a phone call. So there is absolutely at least 2 types of ways to solving the problem: face to face, remotely. This is the way you choose to solve the problem. Second, the algorithm you use. Okay, let's say we choose the remotely method to send the invitation information. As I have said before, you can write a letter and post it. This is method 1. Method 2, you can edit a short message. Method 3, you can use WhatsApp app. You can send a message on WhatsApp app. Method 4, you can make a phone call. Yes. And some other method. So this is the difference of algorithm you choose to use. Okay, let's assume you choose to write a short message. You choose to write a short message. To send a you choose to edit a short message and send the message from your cell phone. The third factor is the implementation by the engineer. When you choose to edit the message, how will you edit the message? You can use simple words just with what, when, how, who to describe your invitation. This is simple enough and meaningful. And you can choose to write a chapter of this. Okay, you can describe your friendship before and predict how you are going on in the future, and describes the weather of today, describes the food on the dinner, and something others. So you can write a lot of sentences. Even you can make this lower. So this is the implementation. This is the difference of implementation by the engineer. Finally, the fourth factor, the EDA tools we use. This may cause a difference. Let's take the same example to explain. You have chosen to send short message, but there is still many choices. There is still many choices of how to send the short message, such as there is many telecom vendors in your country. You have to use the telecom service of company A, or company B, or company D. Each company with different price and different service quality. Yes, if you choose a bad company, you choose a terrible company, the message may be corrupt, or the message may be lost. Okay. Okay, this is just an example, or this is, you can take it as just a joke. But if you are decided to go on with this course, I think you are going to making jokes. But this will be not a big problem. Making jokes or making mistake is the way you are going to professional. Okay, let's go on. Design verification. Design verification is the process that makes sure the IP or SoC design matches design specification. As a function increase in IP SoC, the verification became more and more important and difficult to reach the goal to make it bug-free. So the industry has used some new defined language and methodology to tackle this challenge, such as system Verilog and UVM methodology. UVM methodology, verification methodology. Simulation. Simulation is the process that make your actual design run up in simulation tools. Behavior the same as it will be used in the real world. Usually we use waveform to check or verify and debug the function of the block. DUT, design under test, usually is the IP or SoC design itself. Test bench. Test bench is a code segment that gives stimulus to the inputs of the DUT and make it run up in simulation tool. And it usually contains code to monitor the output of the DUT to verify the function. So when you do simulation, you have to write DUT. This is the design you must write. And to make the design run up, you have to write some test bench. Give stimulus to the DUT and monitor the output of the DUT. Then you compile the DUT and the test bench using simulation tool and run them up in the simulation tool. Evaluation. Evaluation is another way of verification. It's usually verify SoC IP functions in real silicon device, such as an FPGA device or hardware emulation equipment. The advantage of the evaluation is the speed. It can speed up by 10,000 times compared to the RTL simulation. This number are not accurate. This is just a range. Not accurate numbers. So usually, if you are doing design not big, you can use an FPGA platform to do the evaluation. But if you are doing some big design, such as the CPU core of your PC, you may use to you define a GPU processor. You may use to hardware emulation equipment to speed up the verification process. These EDA vendors, Synopsys, Cadence, Mental Graphics, they all provide the hardware emulation equipment. Okay, VCS, Mod Sim, Questa Sim, iVerilog, Verilator. These are the names of the simulation tool from different vendors. This is from Synopsys. This from Cadence. This from Mental Graphics. Mental Graphics has been acquired by Siemens. Word is a waveform code review tool that helping debug. This is a common used tool in the industry. LEC, logic equivalence check. That is a methodology to check the design function of two different representations is equal or not. For example, we can check the function of alter design and the get level list to check whether they are function equal or not. A BEAST, built-in self-test. This is a circuit in the design to test the function of the chip. To test the function of the chip is okay or not. DFT represent for design for test. This is a methodology that puts BEAST logic in a chip. Scan is a DFT method to test the function of combination and sequential logic. Scan is a DFT method. MBEAST, memory BEAST, just memory built-in self-test. This is also a DFT method to test the function of memory macros. So this DFT and BEAST, you can treat DFT BEAST as methodology, and scan memory BEAST as the detailed method to implement the methodology. So the question here is why we need put some BEAST circuit in the chip. This is because the foundry may make some this is because the chips go out from the foundry may not all work well. Some chips will work well while the others are not. So we have to find a method to identify which chip is functioning well and which chip is not. So the goal of the DFT is to identify the chips, to identify the function well chips from the bad chips. That is, we can say the foundry can't make sure all the chips released by the foundry, manufactured by the foundry, is functioning well. So we have to use circuit to identify the bad chips. Place and route. This is the back-end design process. This is in the back-end design process. This is the process of placing the gate cells on the die and route the metal wires between the cells to collect them up. Pre-GSIM, pre-gate sim. This is a simulation on the gate level list without cell delay information. That is, the cell. Each logic cell, the actual cell will have delay from the input to this. The delay is the time from the input to go through to the output of the cell. So the real logic, it has delay from the input to the output. Pre-GSIM is ignore the delay. We set the delay to zero, and simulate the function of the late list. Post-GSIM. This is the simulation on the gate level late list with cell delay. So the two are similar, but the difference is whether we use the cell delay or not. So you can imagine this process will be run faster, and this process will be run much slower than pre-GSIM, and they all run slower than the RTL simulation. STA represents for static timing analysis. This is the process to check whether the chip can run at a defined clock frequency or not. For detail, it actually checks the setup hold timing violation for sequential cells. So, whether or not your chip can run up to 500 megahertz, 1 gigahertz, 2 gigahertz, it will depending on the result of STA check. No, that's not accurate. Basically, it's dependent on your design. It's dependent on your design, but STA tool will give you the assurance. Yes, STA analysis will give you the assurance whether your chip can run at that frequency or not. Okay, timing sign off. This is the final STA check process before tape out. SDC, standard delay constraint. This is a timing constraint used in STA. For example, you need to define the clock frequency in SDC. SDC is a constraint to help STA tool to analyze the setup and hold timing of sequential cells. Clock gating. Clock gating is a method to get off the clocks of sequential cells to save power.没有。On-chip bus. On-chip bus is usually a a function block to collect IPs up and enable the data transfer between them. So you have to define some protocol to realize the bus. So APB, AHB, LINE, XI, these are on-chip bus protocol. These protocols are defined by ARM, and you can use it for free. FIFO, first in, first out. This is an architecture of circuit which lets the first writing data be first read out. Data throughput is to calculate how many data bits a circuit can process within a given time, usually a second. Such, for example, if you say the data throughput of a circuit is 1 megabyte. This means the circuit can eat 1 megabyte data in a second. Or you can say the circuit can process 1 megabyte data in a second. Pipeline is a common use hardware architecture to make the circuit process more data. That is improve the data throughput of the circuit. It can improve the data throughput because this method can increase the clock frequency of the circuit. Ping pong is another hardware architecture to improve data throughput, but the two are different. This one mainly increase the clock frequency. This one is mainly omits the hot cycles when the circuit is working. For example, circuit A have to wait for 1 cycle after a cycle. So the utilization of circuit A is 50%. But if you use some ping pong architecture, we can make the circuit to work cycle by cycle. So the utilization of the circuit B is 100%. So you can say the circuit B, the performance of circuit B, or the data throughput of circuit B is better than circuit A. Okay, that's all. This glossary most of the glossary will be deeper explained in the later sections. And here you have just to know what they represent for and have a basic concept of these words. Okay, thank you.